Hello students, in this video we will discuss a general method to find particular integral for linear homogeneous partial differential equation with constant coefficient. So far we have discussed some specific method for finding particular integral when right hand part which is function of xy is in some particular form. It might be function of x plus by, or it might be some function of x raised to power my raised to power n type. In those cases we can apply some specific methods, but other than these we cannot apply those methods. So we discuss a general method which can be applied for any function of xy. So suppose we have a general equation capital F d, a function of d and d prime. Here d is del by del x and d prime is del by del y is equals to function of xy. To apply general method, first we factorize f dd prime. So suppose if it is of nth order equation, so it has an factor. Suppose d minus m1 d prime, d minus m2 d prime, and so on, d minus m and d prime. Now we will find particular integral which is 1 upon f dt prime of function of xy. Now write f dd prime using this factorization. 1 upon d minus m1 d prime, d minus m2 d prime into so on d minus m and d prime function of xy. Now we will find particular integral of function of xy about each fraction one by one. It means if we have n factor, we are to find particular integral of function of xy about first factor, then whatever result we get, whose particular integral we will find about another factor. So after each step, whichever result we obtained, whose particular integral we will be find about the next factor using the two formulas, which is first is 1 upon d minus md prime function of xy. This is equals to integration of f of x comma c minus mx dx. Here we replace y with c minus mx, that is here c is equals to y plus mx. When we have factor d minus md prime type, in that case we assume c is equals to y plus mx, or we replace y as c minus mx, so c minus mx type. And if we have a factor like d plus md prime, in that case 1 upon d plus md prime function of xy is equals to integration of function of x comma c plus mx, that is we replace y with c plus mx dx. Here c is y minus mx. So we will use these two formula to find particular integral of function of xy. So let's have some problem. So first is d square minus dd prime minus 2d prime square z is equals to y minus 1 exponential x. First we write its auxiliary equation to find complementary function, which is m square minus m minus 2 is equals to 0. Its factor are m plus 1 m minus 2, that is m is equals to minus 1 and 2, about which CF can be written as phi 1 y minus x plus phi 2 y plus 2x. As we have to write auxiliary equation, we replace d with m and d prime with 1. So here we will write in place of m we will write d, and in second term, which is constant part, here we multiply with d prime, so it becomes d plus d prime. It becomes d minus 2d prime. It means d plus d prime and d minus 2d prime are the factor of given equation. So f dd prime is equals to d plus d prime into d minus 2d prime. So about these two factors we will find particular integral of right hand part one by one. Here pi will be 1 upon d square minus dd prime minus 2d prime square for y minus 1 into exponential x. So or factor this term, it becomes 1 upon d plus d prime into d minus 2d prime. Now first we find pi of y minus 1 exponential x with respect to d minus 2d prime. So now we will solve this part only using the formula 1 upon d minus md prime, which we have already discussed above. 1 upon d minus md prime function of xy is equals to integration of function of x. Now replace y with respect with c minus mx. So it becomes function of x comma c minus mx. Here c is y plus mx. Now using this formula, this term become 1 upon d minus 2d prime y minus 1 exponential x is equals to integration. Here this is function of xy. So here replace y with respect to c minus mx. Here m is 2. D minus md prime, d minus 2d prime. So m is 2. So here we replace y with respect with c minus 2x. So it becomes c minus 2x, then minus 1 into exponential x. Now we will integrate it with respect to x. After integration, we get c minus 1 exponential x minus 2 integration x exponential x dx. We can integrate it using by parts. It gives us x exponential x minus x, and when we solve it, we get c minus 1 plus 2 exponential x minus 2x exponential x. When we solve it, we get c plus 1 exponential x minus 2x exponential x, and now we will replace c with y plus 2x. So it gives us y plus 2x plus 1 exponential x minus 2x exponential x. This 2x cancel out. So finally it becomes y plus 1 exponential x. So pi of y minus 1 exponential x with respect to 1 upon d minus 2d prime is y plus 1 exponential x. Now putting this value in equation number 1, that is its value is y plus 1 exponential x. So now we will put here y plus 1 exponential x. Now pi is equals to 1 upon d plus d prime y plus 1 exponential x. So using 2 in 1, pi become 1 upon d plus d prime for y plus 1 exponential x. Now using the formula 1 upon d plus md prime, function of xy is equals to function of x c plus mx dx. Here c is y minus mx. Here in d plus d prime, value of m is 1, so it becomes c plus x. So replace y with c plus x. It gives us c plus x plus 1 exponential x dx. Here c is y minus mx, m is 1, so c is y minus x. Using by parts, we will integrate it, and after integration we get c plus 1 exponential x plus x exponential x minus exponential x. When we solve it, we get y exponential x. So pi of given right hand part is y exponential x. So complete general solution will be z is equals to cf plus pi, which is equals to phi 1 y minus x plus phi 2 y plus 2x plus y exponential x. Here phi 1 and phi 2 are arbitrary function. Let's take one more problem. R plus s minus 6t is equals to y cos x. As we know, R stands for del 2z upon del x square, s del 2z upon del x del y, and t is del 2z upon del y square. We can write del by del x as capital D and del by del y as d prime. So this becomes t square plus dd prime minus 6t prime square is equals to y cos x. Its auxiliary equation is m square plus m minus 6 is equals to 0. So m plus 3, m minus 2 are its factor. So m is equals to minus 3 and m is equals to 2 are roots of this auxiliary equation. So complementary function is phi 1 y plus 2x plus phi 2 y minus 3x. Now to find particular integral, first we are to factorize it. Its factor will be replace m with d and here multiply with d prime. So it gives us d plus 3d prime, d minus 2d prime. So d plus 3d prime and d minus 2d prime are its vector. So pi is equals to 1 upon d plus 3d prime, d minus 2d prime of y cos x. Now first we find pi for y cos x about 1 upon d minus 2d prime. So taking 1 upon d plus 3d prime outside and solve this part using the formula 1 upon d minus md prime. So it becomes 1 upon d minus 2d prime y cos x is equals to, in place of y we will replace c minus 2x. So it becomes c minus 2x into cos x dx. Now we will integrate it with respect to x. Using y parts, when we integrate it, it gives us c minus 2x sin x minus 2 cos x. Here c is what? Y plus mx, that is y plus 2x. So replace c with y plus 2x, it gives us y sin x minus 2 cos x. Now we will replace this part with y sin x minus 2 cos x, hence this equation 1 becomes pi is equals to 1 upon d plus 3d prime y sin x minus 2 cos x. Now we will, using the formula 1 upon d plus md prime, so here we replace y with c plus 3x, so it gives us c plus 3x sin x minus 2 cos x. Now we will integrate this. After integration we get minus c plus 3x cos x plus sin x. After integrating and after solving we get minus 3 plus c plus 3x cos x plus sin x. Now replace c y minus 3x, it gives us minus y cos x plus sin x. So this is pi for right hand part. So z is equals to phi 1 y plus 2x, phi 2 y minus 3x minus y cos x plus sin x. This is general solution. Here phi 1 and phi 2 are arbitrary function. These are some problem based on these methods. So that's all about how to find particular integral for given linear homogeneous partial differential equation with constant coefficient. Thank you.